Welcome, everyone. Today we move deeper into solving vehicle dynamics. Specifically, we will understand the use of Earth-fixed coordinate system, dynamic axle load transfer, and how to use the vehicle equations of motion for solving the problems on vehicle dynamics. Whenever a vehicle accelerates, brakes, or corners, forces and moments shift between the axles. Understanding this weight transfer is fundamental to predicting handling, stability, steering feel, and even crash performance. Now let us begin to solve problems on vehicle dynamics. Let us discuss a problem on vehicle motion with steering. In this problem, we study a car treated as a rigid body moving on a flat road. The vehicle is acted on by traction force from the wheels, aerodynamic drag, braking force, and rolling resistance. At the same time, a constant front wheel steering angle causes the car to move in both the forward and sideways directions. This creates coupled longitudinal and lateral motion, meaning straight line motion and turning motion happen together. Our analysis follows 4 clear steps. First, compute all forces acting on the vehicle, including driving, resistance, and tire forces. Second, use these forces to find accelerations in the vehicle body frame along the forward and sideways directions. Third, transform these accelerations from the vehicle frame to the earth frame, accounting for vehicle orientation. Finally, integrate acceleration over time to obtain velocity, and then integrate velocity to find the vehicle position and path. This structured approach allows us to fully predict how the vehicle moves during a steered maneuver under real-world forces. We begin by listing all given vehicle parameters. These include vehicle mass, wheelbase, center of gravity offsets, aerodynamic properties, and tire force coefficients. We also specify the initial conditions such as vehicle speed, yaw angle, yaw rate, and starting position. 2 coordinate systems are used in the analysis. The body fixed frame moves with the vehicle. Its x-axis points forward and its y-axis points to the left. All forces, traction, braking, drag, and tire forces are defined in this body frame. The earth fixed frame is stationary. Its x-axis points east and its y-axis points north. Vehicle velocity, position, and trajectory are finally expressed in this frame. The key idea is simple. Forces are computed in the body frame, but motion and path are described in the earth frame. We begin by identifying all longitudinal forces acting on the vehicle in the body frame along the forward direction. There are 4 contributors. First is the engine traction force, which pushes the vehicle forward. Second is aerodynamic drag, which grows with speed and always opposes motion. Third is rolling resistance, a nearly constant force resisting tire. Fourth is the braking force, which also acts opposite to forward motion. These forces combine to form the net longitudinal force. Spoken mathematically, the net forward force equals traction force minus aerodynamic drag minus rolling resistance minus braking force. This net force determines the longitudinal acceleration of the vehicle and sets the foundation for the equations of motion that follow. To model lateral forces, we use the bicycle model, which combines the left and right tires on each axle into a single equivalent tire. The front lateral tire force depends on the front cornering stiffness, the steering angle delta, the vehicle side slip, and the yaw rate. The rear lateral tire force depends on the rear cornering stiffness, the side slip, and the yaw rate. In words, each lateral force is proportional to its slip angle, and each slip angle is set by steering input and vehicle motion. These front and rear forces are then added together. Spoken mathematically, the total lateral force equals the front lateral force plus the rear lateral force. This completes the force description needed before writing the vehicle's lateral and yaw motion equations. We now apply Newton's laws of motion in the vehicle body frame. This results in 3 coupled differential equations that govern vehicle motion. First is the longitudinal acceleration. Spoken mathematically, the forward acceleration equals the net forward force divided by mass plus the product of yaw rate and lateral velocity. This shows that turning motion can influence forward acceleration. Second is the lateral acceleration. Spoken mathematically, the sideways acceleration equals the net lateral force divided by mass minus the product of yaw rate and forward velocity. This term represents the apparent force felt in a rotating frame. Third is the yaw dynamics equation. Spoken mathematically, yaw moment of inertia times yaw acceleration equals the front lateral force times distance A minus the rear lateral force times distance B. Together, these equations show that longitudinal motion, lateral motion, and rotation are fully coupled. The yaw rate links motions that would otherwise be independent, making vehicle dynamics inherently interconnected. So far, all forces, velocities, and accelerations were written in the vehicle body frame. To track the vehicle's actual path on the road, we must convert them into the earth frame. This is done using a two-dimensional rotation matrix based on the yaw angle, spoken as PSI. Spoken mathematically, earth frame components are obtained by multiplying the body frame vector by a rotation matrix made of cosine PSI and sine psi terms. The matrix rotates vectors by the yaw angle without changing their magnitude. This works because the matrix is orthogonal, meaning it preserves length and energy. After rotation, body frame forward and sideways motions become eastward and northward components in the global frame. This transformation allows us to move from vehicle-centric physics to map-level motion, which is essential for trajectory prediction, navigation, and simulation. Once acceleration is known in the earth frame, we determine the vehicle's motion through time integration. First, earth frame acceleration is integrated over time to obtain the earth frame velocity as a function of time. Next, this velocity is integrated again over time to obtain the earth frame position, starting from the initial origin. Spoken mathematically, velocity is the time integral of acceleration, and position is the time integral of velocity. This process is cumulative, meaning small errors can build up over time. Accurate results therefore depend on using a sufficiently small time step, especially when the vehicle follows a curved path due to steering. This final step converts forces and accelerations into the actual trajectory of the vehicle on the road. This analysis produces 4 key results. First, we obtain the time history of all individual forces, showing how traction, resistance, and tire forces evolve. Second, we compute the acceleration vectors in the vehicle body frame, revealing how forward and sideways accelerations interact. Third, these accelerations are transformed and integrated to give the earth frame velocity over time. Finally, integrating velocity gives the vehicle's XY trajectory on the ground. A constant steering angle creates a sustained lateral force, which produces a curved path and steady sideways displacement, exactly matching expected real-world vehicle behavior. This confirms that the model is physically consistent and correctly captures the link between forces, motion, and trajectory. Let us define all vehicle and environment parameters used in the analysis. These values anchor every calculation that follows. The vehicle has a mass of 1,500 kilograms and a yaw moment of inertia of 3,000 kilogram meters squared. The center of gravity is located 1.2 meters from the front axle and 1.5 meters from the rear axle. Both the front and rear tires have a cornering stiffness of 80 kilonewtons per radian. For aerodynamic effects, the air density is 1.225 kilograms per cubic meter, the drag coefficient is 0.32, and the frontal area is 2.2 square meters. Rolling resistance is modeled using a coefficient of 0.015. The vehicle applies a constant traction force of 3,000 newtons, with no braking force. The front wheels are steered at 5 degrees. The simulation advances in time steps of 0.1 second, spoken as delta t equals 0.1 second. Together, these parameters fully define the vehicle, the environment, and the operating condition for the dynamic step-by-step vehicle solution. The start of the simulation, the vehicle is placed at the global origin, with x equals 0 and y equals 0. The vehicle heading angle, spoken as PSI, is 0 radians, meaning the car is aligned with the earth frame. The longitudinal speed is 15 meters per second. The lateral speed is 0, and the yaw rate is also 0. These 6 initial values, position, heading, velocity, and rotation, form the complete kinematic starting point. From this state, all future motion is generated through the first and subsequent time integration steps. We first compute the resistive forces acting against motion, the aerodynamic drag, and next the rolling resistance. Both resistive forces act opposite to motion. Starting from a traction force of 3,000 newtons, we subtract drag and rolling resistance. Spoken mathematically, net longitudinal force equals traction minus aerodynamic drag minus rolling resistance. This gives a net body frame longitudinal force Fx equals 2,682 newtons. This force is the direct driver of forward acceleration in the vehicle. At the initial moment, the lateral velocity is 0, and the yaw rate is also 0. Because of this, the front slip angle is set entirely by the steering input. The steering angle of 5 degrees corresponds to 0.0873 radian. The rear slip angle is 0 since there is no sideways motion or rotation yet. Lateral tire force is computed as cornering stiffness multiplied by slip angle. Using a cornering stiffness of 80 kilonewtons per radian, the front lateral force becomes 6,984 newtons, while the rear lateral force remains 0. Adding front and rear contributions, the total lateral force equals 6,984 newtons, acting at the front axle. This lateral force initiates the vehicle's sideways motion and starts the turning response. We now compute the vehicle accelerations using Newton's laws. The longitudinal acceleration is found by net forward force divided by mass, which gives 1.729 meters per second squared. The lateral acceleration is found by net lateral force divided by mass, which results in 4.66 meters per second squared. Next, we compute the yaw acceleration from moment balance. Substituting values gives a yaw acceleration of 2.729 radians per second squared. These three accelerations, forward, sideways, and rotational, define how the vehicle's velocities will change during the next 0.1 second time step. We now update the vehicle states using explicit Euler integration over a 0.1 second time step. The longitudinal velocity increases from 15 to 15.18 meters per second. The lateral velocity, which was initially 0, now appears as 0.47 meters per second. The yaw rate increases to 0.279 radians per second. The heading angle, spoken as psi, advances by 0.0279 radians. At this point, the body frame motion includes forward speed, sideways motion, and rotation, marking the start of a true turning maneuver. To express motion in the Earth-fixed frame, we rotate the body frame velocities using the current yaw angle, which is 0.0279 radians. This rotation uses a 2x2 direction cosine matrix made of cosine psi and sine psi terms. This gives V capital X equals 15.16 meters per second and V capital Y equals 0.89 meters per second. This transformation projects the vehicle's motion into the global Earth frame, which is required to compute the vehicle path and trajectory. To update the vehicle position, we multiply the Earth frame velocities by the time step, which is 0.1 second, giving a displacement of 1.5 to 2 meters along the X direction and 0.089 meters along the Y direction. These displacement increments are added to the initial position at the global origin. After 0.1 seconds, the vehicle is now located at X equals 1.52 meters and Y equals 0.089 meters. This completes one full integration step from initial conditions to updated spatial coordinates. At the end of this time step, the vehicle force and motion results are summarized. Together, these values confirm that the force, acceleration, rotation, and position calculations are consistent and ready for extension into multi-step simulation or experimental comparison. At time 0.2 seconds, we begin the next hand calculation step using the vehicle state carry forward from 0.1 seconds. No simulation software is used here. Each force, acceleration, velocity, and position will again be computed manually using these updated states. Aerodynamic drag is calculated using dynamic pressure and equals 99 newtons. Rolling resistance based on tire normal load equals 221 newtons. Both resistive forces are subtracted from the drive force of 3,000 newtons. This gives a net longitudinal body frame force, Fx equals 2,680 newtons, which accelerates the vehicle forward. Because the vehicle now has side slip and yaw, both axles develop slip angles. The front slip angle, alpha F, equals 0.0342 radians, coming from steering input minus the side slip effect. The rear slip angle, alpha R, equals minus 0.0033 radians, caused by axle geometry. Using cornering stiffness, these angles generate a front lateral force of 2,736 newtons and a rear lateral force of minus 264 newtons. Together, they produce a total lateral force, Fy, equals 2,472 newtons. Because the vehicle is rotating, accelerations are coupled. Longitudinal acceleration AX equals 1.92 meters per second squared, including a plus 0.13 coupling contribution. Lateral acceleration AY equals minus 2.59 meters per second squared, reduced by 4.23 due to coupling. Yaw acceleration R dot equals 1.23 radians per second squared, produced by the difference in front and rear moment arms. Using an Euler integration over delta t equals 0.1 seconds, body velocities are updated. Longitudinal speed Vx increases to 15.37 meters per second due to positive acceleration. Lateral speed Vy reduces to 0.21 meters per second as rotational coupling dominates lateral force. Yaw rate R rises to 0.42 radians per second, setting the vehicle state for the next coordinate transformation. Body frame velocities are rotated into the global frame using the yaw angle TSI equals 0.0681 radians. Applying the two-dimensional rotation matrix, Vx equals 15.37 and Vy equals 0.21 meters per second project to earth frame speeds. The result is V capital X equals 15.32 meters per second, mostly forward, and V capital Y equals 1.25 meters per second, indicating growing lateral motion. These global velocities are now ready for position integration. Using the earth frame velocities, position is updated over delta t equals 0.1 seconds. The global x position increases from 1.5% 2 meters to 3.05 meters, while the y position advances from 0.089 meters to 0.214 meters. After this second manual integration step, the vehicle is located at x equals 3.05, y equals 0.214 meters, showing accumulated yaw and side slip during the turn. This table summarizes the vehicle state after 0.2 seconds, providing a compact reference for all computed states. We will answer the question, why coupling terms now dominate? At time t equals 0, both yaw rate and lateral velocity were 0, so the coupling terms r times Vy and r times Vx contributed nothing. By t equals 0.1 seconds, yaw rate and lateral motion are present, injecting plus 0.13 meters per second squared into longitudinal acceleration and minus 4.23 meters per second squared into lateral acceleration. This shows why body frame equations seem complex. Once the vehicle starts rotating and slipping sideways, the coupling terms quickly become numerically dominant and strongly shape the motion. Now let us examine what happens at 0.2 seconds when the steering wheel is instantly returned to zero angle. This sudden removal of steering input creates a classic step steer release condition. During the following 0.1 second, the vehicle no longer receives commanded lateral input, but it still has residual yaw rate and sideways velocity. These remaining motions generate lateral tire forces, which naturally act to stabilize the vehicle. The current body frame velocities and the global position at 0.2 seconds serve as the starting point for this open loop recovery response, showing how the vehicle settles on its own without further steering input. At time 0.2 seconds, the vehicle continues from the previous calculation step. The forward speed Vx is 15.37 meters per second, and the sideways speed Vy is 0.21 meters per second. The vehicle is rotating with a yaw rate R of 0.402 radians per second, and its heading angle PSI is 0.0681 radians. In the global reference frame, the vehicle is located at x equals 3.05 meters and y equals 0.214 meters. Together, these values define the initial condition vector for the steering release interval and directly control how the tire slip angles are computed in the next step. The vehicle continues to receive a propulsive force of 3,000 newtons. This is opposed by aerodynamic drag of 101 newtons and rolling resistance of 221 newtons. Subtracting these losses leaves a net longitudinal force of 2,678 newtons, called Fx. This remaining force drives forward acceleration. Because aerodynamic drag increases with the square of vehicle speed, it naturally limits acceleration and creates a speed-dependent decay effect that shapes longitudinal motion during the steering release phase. With the steering angle set to 0, lateral tire slip is no longer commanded by the driver. The front slip angle is calculated as minus 0.0452 radians. The rear slip angle is computed as plus 0.256 radians. Although steering input is removed, these non-zero slip angles arise from residual yaw rate and side slip. They generate lateral tire forces that automatically self-center the vehicle, initiating natural stabilization of the trajectory. With a cornering stiffness of 80 kilonewtons per radian, the slip angles generate lateral tire forces. The front lateral force equals minus 3,616 newtons. The rear lateral force equals plus 2,048 newtons. Adding front and rear forces yields a net lateral force of minus 1,568 newtons. This negative side force acts opposite the lateral motion, pulling the vehicle back toward its velocity direction. As a result, side slip is reduced and the vehicle naturally stabilizes, explaining the yaw and side slip decay after steering release. Using the Newton-Euler equations, we now compute the vehicle accelerations in the body frame. The longitudinal acceleration equals 1.87 meters per second squared. The lateral acceleration equals minus 7.23 meters per second squared. The yaw acceleration comes from the tire moment balance, yielding minus 2.47 radians per second squared. Together, these accelerations show how propulsion, lateral tire forces, and yaw moments combine to update the vehicle's velocity and rotation during the steering release response. Using an explicit Euler integration with a time step of 0.1 seconds, the vehicle state is advanced to 0.3 seconds. The longitudinal velocity increases slightly to 15.56 meters per second due to continued net traction. The lateral velocity drops in reverses sign to minus 0.51 meters per second, indicating decay of side slip after steering release. The yaw rate decreases to 0.155 radians per second, showing rotational damping. The heading angle advances to 0.0836 radians. This step captures the first-order reduction of lateral and yaw motion, while forward speed continues to build. The body frame velocities are rotated into the earth frame using the yaw angle rotation matrix. This gives an eastward velocity of 15.54 meters per second and a northward velocity of 0.79 meters per second. Integrating these velocities over 0.1 seconds updates the global position to x equals 4.60 meters and y equals 0.293 meters. The small lateral velocity reflects remaining side slip, while the larger forward component continues to carry the vehicle along its current heading. Even though the steering angle is now 0, the tires still generate lateral forces because the vehicle has remaining yaw rate and side slip. These forces oppose the motion, reducing the yaw rate from 0.402 to 0.155 radians per second and reversing the sign of the lateral velocity. This loss of rotational and lateral energy is known as yaw side slip decay, showing how tire elasticity and vehicle inertia naturally work together to bring the car back towards straight line stability after the driver releases the steering wheel. At time equal to 0.3 seconds, the steering angle remains fixed at 0, and the vehicle is continuing its post-release recovery. This slide captures the exact state of the car at this instant. The longitudinal speed Vx is listed, along with the lateral speed Vy, the yaw rate R, and the heading angle psi. The global position is defined by x and y coordinates in the earth frame. Together, these 6 values fully describe the vehicle's motion at this moment and serve as the starting point for computing the next 0.1 second time step. Using the idea of longitudinal force balance on the vehicle. First, aerodynamic drag is computed as 104 newtons. Next, rolling resistance is recalled as 221 newtons. Both resistive forces are subtracted from the 3,000 Newton drive force. This results in a net longitudinal force Fx equals 2,675 newtons. This net force is the sole driver of the vehicle's upcoming forward acceleration. Even when the steering angle is 0, the vehicle can still experience tire slip. This happens because there is a sideways velocity called Vy and a yaw rate, which means the vehicle is rotating slightly. The front slip angle, called alpha f, and the rear slip angle, called alpha r, are calculated using kinematic ratios. In words, this means the slip angles come from the ratio of sideways motion and rotational motion to the forward speed of the vehicle. For this case, the front slip angle is 0.0208 radians, and the rear slip angle is 0.0478 radians. Even though these angles are small, they are important. They allow the tires to generate lateral forces, which continue to gently push and guide the vehicle sideways. Let us now look at lateral force summation. Using cornering stiffness, we convert tire slip angles into lateral forces. Assuming a linear tire stiffness of 80 kilonewtons per radian, the front tire generates a lateral force of 1,664 newtons. The rear tire generates a lateral force of 3,824 newtons. Adding these together, the total lateral force becomes 5,488 newtons. This combined force represents the side push acting on the vehicle. It appears directly in the lateral equation of motion and works to counter the remaining side slip velocity of the vehicle. Let us now look at the acceleration triad: longitudinal acceleration, lateral acceleration, and yaw acceleration. Using Newton's laws and Euler's equations, these accelerations are assembled. The longitudinal acceleration, AX, depends on the remaining tractive force, and it also includes a Coriolis effect caused by vehicle rotation. The lateral acceleration, a Y, is governed by the tire side forces and is balanced by the product of yaw rate and longitudinal velocity, often spoken as R times Vx. The yaw acceleration comes from the difference in moment arms between the front and rear lateral tire forces. This imbalance produces a damping yaw acceleration of minus 1.25 radians per second squared. Together, these three accelerations fully describe how the vehicle translates and rotates during a maneuver. Let us now look at state integration. We use a first-order Euler integration with a time step of 0.1 seconds and update the states up to 0.4 seconds. During this step, the body frame longitudinal velocity, Vx, increases to 15.73 meters per second due to the applied tractive force. At the same time, the lateral velocity, Vy, decreases and moves closer to zero as the side slip motion is gradually damped. The yaw rate also decays and reaches 0.03 thousand radians per second. Finally, the yaw angle, CSI, increases slightly by 0.003 radians. This small yaw angle change prepares the vehicle state for coordinate transformation from the body frame to the earth-fixed reference frame. Next, we perform the earth frame projection by rotating and translating the vehicle position, using the rotation matrix form from the yaw angle CSI equal to 0.0866 radians. The body frame velocities are transformed into earth frame components. After rotation, the global x direction velocity, V capital X, becomes 15.71 meters per second, and the global y direction velocity, V capital Y, becomes 0.98 meters per second. These velocities are then multiplied by the time step, delta t, to obtain the position increments. As a result, the global position advances to x equals 6.17 meters, and y equals 0.391 meters. This step completes the mapping from vehicle motion to its position in the global reference frame. Let us now look at the final outcome and key insight. At time equal to 0.4 seconds, the final state table is shown, listing the vehicle's velocities, yaw rate, orientation, and position. The key takeaway is this: there is zero steering input, yet the vehicle naturally returns to a straight path. This self-alignment occurs because inertial lag and tire cornering stiffness work together to dissipate side slip and yaw energy. As a result, the vehicle stabilizes on its own, demonstrating the effect of natural damping in lateral dynamics. Let us summarize the state evolution. The vehicle state at every 0.1 second from t equals 0 to t equals 0.4 seconds. Each row lists the longitudinal and lateral forces, accelerations, body frame velocities, yaw rate, yaw angle, and earth frame position. The table clearly shows how the vehicle responds immediately after steering is applied, followed by a transient decay once steering input is removed. This time, history confirms how forces generate motion, motion creates coupling, and coupling governs the vehicle's short-term dynamic response. Once lateral velocity 5y and yaw rate r become non-zero, the body frame coupling terms activate, injecting additional components into both longitudinal and lateral accelerations. After the steering input is released, the tire lateral forces naturally realign the vehicle, reducing side slip and yaw rate. This self-correcting behavior demonstrates the inherent damping and stability predicted by the linear bicycle model. To analyze the complete maneuver, the same 0.1 second step procedure can be repeated forward in time. Each step recomputes tire forces, body frame accelerations, velocity updates, and earth frame position. Automating this loop allows states to be stored, trajectories to be visualized, and longer transients or driver-in-the-loop maneuvers to be evaluated efficiently. Let us recap the procedure once again. First, define vehicle mass, inertia, geometry, tire stiffness, aero and rolling losses, drive force, initial velocities, yaw rate, yaw angle, position, and time step delta t equal to 0.1 seconds. For computing the initial response from 0 second to 0.1 second, compute drag, rolling resistance, longitudinal force, slip angles, tire forces, and accelerations. Update velocities, yaw, transform to earth frame and advanced position. For computing the coupled dynamics from 0.1 second to 0.2 second, recalculate forces using non-zero lateral velocity and yaw rate. Include coupling terms RVY and RVX. Update accelerations, velocities, yaw, and position. For computing the steering, release dynamics from 0.2 second to 0.3 second. Set steering angle to 0. Residual side slip and yaw. Generate tire forces that drive decay in lateral motion and rotation. For computing the natural damping dynamics from 0.2 second to 0.3 second, with zero steering, coupling, and tire forces continue to reduce yaw rate and side slip while the vehicle advances along a stabilized path. The final takeaway from the problem is a step-by-step integration exposes force coupling and shows how tire moments naturally stabilize the vehicle, which is the core insight for vehicle dynamics and control design. See you again in another topic on vehicle dynamics. Thank you.